Chapter 4 is on radicals, and so the first section is on introducing again entire and mixed radicals. So last year you learned a little bit about radicals, and just kind of review a little bit of that first. So the index is the number that is in the little crevice there, I guess, of the radical sign, your radical sign, so that here's your index. And then you've got your radical symbol, which is that sign. And then underneath the radical sign is your radicand. And the whole thing is referred to as a radical. All right, so, and the other thing you remember is when you have a square root, it's understood that the index is a 2. It's not usually written there. So let's just answer the questions here at the bottom. First one, identify the index and radicand for each radical. So the first one, the index would be 4, and the radicand is the number underneath the radical symbol, which is 35. The second one, the index is 3, and the radicand would be 28. And the last one, the index is understood to be a 2, and the radicand would be 8. Square roots. The square root of a number x is the number which, when multiplied by itself, equals the value of x. So we're going to do a little investigation now. If you take two numbers that are opposites of each other, for example, -4 and 4, and square both those numbers, you should notice that both answers are the same. So what does this imply about the square root of a positive number? It implies that there are two square roots. And if we look at our example for 16, for example, 16 has square roots of 4 and -4. Okay, so when we're referring to the square roots, the principal square root is your positive answer. And that's when we use the little symbol, the square root symbol that you're familiar with, this symbol right here. So when we see that symbol, we're only interested in the positive square root of the number. The negative square root is called the secondary square root, and it would be the negative of the principal square root, basically. All right, so sometimes, when we're dealing with situations, it's really only the principal square root that makes sense. For example, if you're talking about finding the side length of a right triangle and you're using Pythagorean theorem, part of the Pythagorean theorem would involve you taking, when you solve it, you would end up taking the square root of a value, and you wouldn't even be interested in the secondary square root because you're talking about the length of a side. All right, so let's try a couple of these questions. First one, what is the secondary square root of 36? So when it's a secondary square root, we're looking for the negative square root. So that would be the -6, because -6 times -6 will give you 36. And what's the principal square root of 81? Principal would be the positive square root, so that would be 9, since 9 times 9 is 81. All right, so number 3, we have to evaluate each of the following. So the first one has the negative outside the square root sign. So it would be the negative of the square root of 100, which is -10. B is the square root of 9, which is just going to be 3, since 3 times 3 is 9. And the last one, we're finding the square root of a -49, and this would be not real, because you cannot find, there is no number which, when multiplied by itself, will give you a negative value. It's either going to be a positive times a positive to give you a positive, or a negative times a negative to give you a positive. So there's no way you can multiply the same number by itself and get a negative value. So there is no square root of negative numbers. So this leads us to this little point here, the first point, that negative numbers do not have a square root in the real number system. So that means basically the square root of a negative number is not real. Perfect square numbers, such as 1 and 4, 9, 16, and so on, have square roots which are rational numbers. So when you take the square root of 4, you get 2. You take the square root of 9, you get 3, and so on. Non-perfect square numbers, such as 17 and 29 and those ones, when you take the square root of those, they're not perfect square numbers, so they would be called irrational numbers. And irrational numbers, if you remember, are numbers which, in terms of their decimal form, do not repeat or terminate. Cube roots are defined as being, the cube root of a number is defined as being the number which when multiplied by itself 3 times equals the value of x. So if we investigate cube roots and choose two opposite numbers, for example, 3 and -3, if you cube the numbers, what do you notice? So if you cube the numbers, 3 cubed is going to be 3 times 3 times 3, which is 27. And -3 cubed is going to be -3 times -3 times -3, which is going to be -27. So these aren't the same numbers, same values. So unlike square roots, the cube of a positive and a negative don't result in the same answer. So what does this imply about the cube root of a positive number? It implies that there's only one cube root for a positive number and one cube root for a negative number. So all numbers, both positive and negative, have only one cube root, and it's denoted with the symbol, your radical sign with the little 3 in the index. And cube roots, unlike square roots, cube roots of negative numbers are defined, and they would be negative. So we're going to do a few questions here now. So first one, evaluate. Cube root of 64 would be 4, since 4 times 4 times 4 is 64. And the cube root of -8 would be -2, since -2 times a -2, it kind of looks like 12, -2 times -2 times a -2 is -8. And the cube root of 125 would be 5, since 5 times 5 times 5 is 125. And the cube root of -64 would just be -4. And this one here is the negative of the cube root of 125, which is the negative of 5. And the last one here would be the negative of the cube root of -8, which would be -2, because -2 times -2 times -2 gives you -8. And these two negatives then would cancel each other out and give you a resultant answer of +2. All right, so the next topic is on mixed radicals and entire radicals. And again, this is a little bit of review of 1201 math. An entire radical would be basically everything is under the radical sign. There's nothing out in front of the radical. So root 48, root 80, cube root 144, and fourth root of 162 are all examples of entire radicals. Everything, every part of the number is underneath that radical sign. A mixed radical, on the other hand, has a number out front of the radical sign. So 2 root 30 would be an example of a mixed radical. 4 root 5, 2 cube root 8, and 3 fourth root of 2. All these radicals have a number in front of the radical symbol. Okay, Math 1201, we used a multiplication rule for radicals to help us simplify radicals. So we're going to be using that again now. I'm going to be reviewing that. But basically, the rule for radicals is if you have the nth root of a number, and you can break it down into two smaller parts, basically. So if you had the nth root of a product A times B, you could break that down into the nth root of the first part times the nth root of the other part. And that will only work if n is even, meaning like square roots, and that you have to have A and B being positive, because if A and B were negative, they wouldn't be defined. For example, the square root of A is not defined if A is negative. Not defined if, A is negative. All right, so when we use this rule, there's a couple of ways we can do it to help us break down radicals. One is to think of your largest perfect squares or perfect cube factors and break it down that way. Or you could do what's called a prime factorization method. So we'll just go through each one of these types first. You can use whatever one you want to simplify. Most people tend to like this method here of extracting the largest perfect square or perfect cube. But again, in order to use that method, you've got to be familiar with the perfect squares and perfect cubes, so it's a good idea to probably keep this list close by or write it down when you start to do these until you get used to which numbers are perfect squares. So the perfect squares are basically 1 times 1, which is 1, 2 times 2, which is 4, 3 times 3, which is 9, 4 times 4, which is 16, 5 times 5, which is 25, 6 times 6, which is 36, and so on. And cubes would basically be multiplying each of the numbers by themselves 3 times. So 1 times 1 times 1, which is 1. 2 times 2 times 2, which is 8. 3 times 3 times 3, which is 27, and so on. So let's try a few examples using this method. So the first one, if we take 72, so we go to our, I'll just bring this back again a little bit. We go to our list of perfect squares, because it is a square root that we're trying to break down. If we go through the list of perfect squares that are less than 72, and see which of those perfect squares, if any, is a factor of 72, we find that 36 is a factor of 72, and it's the largest perfect square factor. So the square root of 72 could be broken down into the square root of 36 times 2, because 36 times 2 is 72. And then you could just basically use your multiplication rule that we had above and break that up into 2 separate radicals, which is 6, square root of 36 now can be replaced with the whole number 6, root 2. Now, if you didn't take the perfect square factor, because sometimes people will break it down as 9 times 8, you will get the same answer eventually, but you'll have to do a few more steps, because the square root of 9 is 3. But when you break down the 8 can be broken down into perfect square factor 4 times 2. So that would basically require you adding a few extra steps to your solution. But in the end, you would end up with 6 root 2 the same way. Oops, not root 6, root 2. Okay, so there's 2 ways you can do it. I usually try to get the largest perfect square factor, and you have less steps. Okay, so for B though, we'd be trying to extract the largest perfect cube factor. So if you look at your list of numbers that are less than 250, the biggest perfect cube that is a factor of 250 would be 125. So you would break that down as the cube root of 125 times 2. Which then you can separate as the cube root of 125 times the cube root of 2, which is 5 cube root 2. Now, the other method is using prime factorization, and what that basically involves is breaking down the radicand into its product of prime factors. And then any factor that occurs in a pair would be basically taken outside the radical sign as part of your perfect square factor. So let's break up the first one, 108. We break it down into prime factors. That's 2 times 54, which is 2 times 9 times 6, which is 2, and that's 3 times 3. And that's 3 times 2. 6 is 3 times 2. So if you look at, this is there 2 times, and 3 is there 2 times. So basically you have, if you put all those ones that have circled together, you've got 2 times 3 times 3 times 2, which is 9 times 4, or 36. And then you got that 3 left over here. So it's 36 times 3. So 36 would be the biggest perfect square factor of 108. So 36 times 3 is what you would break down 108 as, and that would give you the square root of 36 times square root of 3, which is 6 root 3. And similarly, you do that for the cube root as well, so you'd break that down, but this time you'd be looking for prime factors that occur 3 times and put them together as your largest perfect cube factor. So this would be 9 times 8, and then that would be 3 times 3, and this would be 2 times 2 times 2. So there are 3 2's there, and that means that 8, because the product of those is 8, is the perfect cube factor, the only perfect cube factor of 72. So this would be written as cube root of 72 would be cube root of 8 times 9, which would equal the cube root of 8 times the cube root of 9, which is 2 cube root 9. And we can't break down 9 any further because 9 doesn't have any perfect cube factors. So we'll do some practice examples using both methods, and we'll just practice both of them, but you can use, once you start the questions yourself, you can do whatever one you want. You don't have to show both ways, and you won't be tested on doing one way over the other. All right, so the first one, extracting the largest perfect square. If you look at your list of perfect square factors, I'll just write them over here. Well, 1 is a perfect square, but it's not really helpful to break it down. So 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25, 6 times 6 is 36, and so on. So we don't need to go any higher than that because we're only talking about 24. So if you look at the numbers that are less than 24, are any of those factors of 24? And they are. 4 is, so you would break that down as 4 times 6 is 24. And then that becomes the square root of 4 times the square root of 6, which is 2 root 6. And if you're using prime factorization, you would basically take 24 and break it down into 4 times 6, and break it down into 2 times 2, 2 times 3, and there's 2 2's, because you're talking about square roots, so you're looking for pairs. And that means that 2 times 2, or 4, times the remaining factors are 2 times 3, which is 6. And that would become the square root of 4 times the square root of 6, which is again 2 root 6, because the square root of 4 would be replaced with the 2. 20, if you were to take the square root of 20, if you look at the perfect squares list, 4, 9, 16, 4 also is a perfect square factor of 20. So you'd break that down as 4 times 5, and then that would be the square root of 4 times the square root of 5, or 2 root 5. After a while, you can probably eliminate this step here and just start with, realize that the square root of 4 times 5 would eventually be the 2. Square root of 4 would come out as a 2. Prime factorization method, you would start off with a 20 and break it down into factors. 2 times 10, 2, and then 10 is 2 times 5, and therefore you got 2 2's. So that means your biggest perfect square factor is 4. So you would have the square root of 4 times 5, which is square root 4 times square root 5, or 2 root 5. Same answer. We'll try this method here. And I'm going to just use the method. I basically use the extract the largest perfect square, but sometimes if the number is big, I'll just start to break it down into prime factors because I don't have a large enough list for all the big perfect squares. So this one here, 150, I know that 25 is definitely a factor that is a perfect square factor of 150. So 25 times 6 would be 150. So therefore that would break down as root 25 times root 6, or 5 root 6. And 5 root 24 would be, again, 4 is the biggest perfect square factor of 24, so I'm going to write that as 4 times 6. And then you can write that down as, break it down as root 4 times root 6, which is 5 times 2 root 6. And they get multiplied, the numbers that are out in front, so that would be 10 root 6. The cube root of 80, you'd be looking for the biggest perfect cube factor. So if you think about 88 is a perfect cube factor of 80. So that would be 8 times 10. And then that would be 5 cube root 8 times cube root 10, which is 5 times 2 cube root 10. And then that would be 10 cube root 10. And the last one, 162. If you look at your list of perfect square factors, if you can't remember, just go back to page 52, I think it was. So if you look at the list, 81, I believe, is the largest perfect square factor of 162, 81 times 2, and that would be -7, root 81 times root 2, which is -7 times 9, root 2, which would be -63, root 2. And you should also be able to convert mixed radicals back to entire radicals. So if you reverse the process, if there's a number out front of a cube root sign, you'd have to bring it back in 3 times to put it back under the cube root. And if there's a number out front of a square root sign, you'd have to bring it back in 2 times to put it back into an entire radical. So we're going to try those. So this one here, if you've got 2 square root 7 and you want to put it back as an entire radical, that would mean that it would have been 2 times 2 underneath. Because if you know, it had to be there as a pair to be able to be taken out as a square root. So this would give you 7 times 4, which is 28. And the second one is also a square root, so if you want to bring that, I didn't mean to do that. If you want to bring that back under the square root sign, the 11 is already there, and the 3 would have to come in as 3 times 3, or 9. And that would give you 11 times 9, or 99. The next one is a cube root, so if you want to put it back under the cube root sign, that means it had to be 5 times 5 times 5 in order to have come back outside as a whole number 5. It had to be 5 cubed underneath the radical sign. So that would be the cube root of 2 times 125, or 250. The next one is again a cube root, so if you want to put it back under, it would have to go in 3 times, so 3 3s, because 3 is the number that's out front, and that would be 4 times 27, which is 108. Whoops. Okay. The next one would be again a cube root, so you would want to bring that, where it's a cube root, you can actually bring that negative back under the cube root sign. If it was a square root, you'd have to leave the negative out front, because you can't bring the negative under the square root sign. But in this case, it is a cube root, so we can bring in -3 times -3 times -3, and that would be -27 times 2, or -54. So that would be the cube root of -54. And the last one is the square root sign. So you'll be bringing that half in 2 times, a half times a half. And if you multiply those, you get 48. That's understood to be 48 over 1. So that would be 48 times 1 times 1 over 1 times 2 times 2, which is 4. And that would be the square root. 4 goes into 48 12 times, so it would be square root 12. And that would be simplified, it wouldn't be simplified, but it would be the entire radical. So these are some questions now that you can try on pages 182 to 183 of your text that practice some of these skills.